Hello everyone, welcome to another online lecture for ME5030. This is our fifth lecture, and in this lecture we will be continuing and expanding the idea of Lagrange multipliers by looking at a problem. And by the end of this lecture today, I want to summarize the different types of Lagrange formulations that we have seen, when to use configuration coordinates, when to use generalized coordinates, and so on and so forth. Okay, so plan for today's lecture is the following. Okay, so aim is first thing is to solve a problem using Lagrange multipliers. Okay, solve a problem using Lagrange multipliers. And the second thing is to summarize the Lagrange formulations for different situations. Summary of Lagrange formulation for various situations. All right, the problem that we are going to be solving is another famous problem. Previously we had seen a bead on a hoop. Now this problem is a bead on a tube problem. Okay, so the problem that we are going to be looking at today. Okay, so problem, we are going to consider a bead on a tube. Consider a bead of mass m and placed inside a spinning tube. Tube as shown in the figure below. All right, and here is the situation. So I have the tube which I'm going to draw first. Okay, so here is the tube, one here, and then let me duplicate that and take that and draw here. Just want to create a small slit. Okay, and then extend a branch on here. So all of this is the tube as such. Okay, and then bring that here, and now within this tube I have a bead that is placed as shown. Okay, so here is a bead that is placed as shown. Now this tube is spinning about the vertical axis, so let me draw a vertical axis here. Okay, so here is the vertical axis, and let me draw it using dotted lines. And let's say that the bead itself is called as the point P. So let's call this as point P. This has a mass m as we have specified in the problem, and then this point here I'm going to call it as point O. Okay, so here is point O. That is the point on the tube. It's a fixed point, of course. I'm going to draw a line from the point O to the point P, and that's going to be defined by a position R. Okay, so here is that line that I'm going to be drawing. Straight line, more or less. Okay, and we're going to be calling that as the position R, and this is going to be R of t. Okay, and this signifies that the bead is traveling within the tube confines, and as I said before, the tube is spinning about the vertical axis. Let's say that this is the direction of rotation. Okay, and let's say that the angular velocity is omega, and this omega let's say is the constant value. Okay, so let's write down these details. The tube itself is spinning about the vertical axis as shown. Tube spins about the vertical axis at a constant rate omega. Okay, so that's one thing that is given to us. And the other thing that I also want to mention is that let's say that the surface of the tube, the inner surface where the particle is contacting the tube, is a rough surface. So the contact between the particle or the bead, okay, the bead, which is the particle which we have labeled as P, and the tube is rough, which means that the coefficient of kinetic friction is given as mu k, okay, with the coefficient of kinetic friction given as mu k. All right, so this is another information that is given to us. We are asked to neglect the dimensions of this particle, so this is still behaving as a particle, it's not a rigid body as such. Okay, so neglect the dimensions of the particle and we are also going to say that gravity is acting vertically down, so let me make a note of that and say that okay, this is the direction of positive gravity. Okay, and what are the things that we need to find in this problem? Okay, so obtain. First one, the equations of motion. That characterizes the motion of this bead. Okay, so that's one thing that we want to obtain. Then I also want to obtain the constraint forces. Okay, so obtain the constraint forces using the idea of Lagrange multipliers. Using Lagrange multipliers. Okay, so this is the key thing in this particular problem. We need to use the idea of Lagrange multipliers, and then we need to find the equations of motion as well. And if we have time, we will discuss certain conditions for incipient forward motion of the particle. Okay, so if there is time, we will do the following, if time permits. Okay, we will discuss the condition for incipient forward motion of the particle within the tube. All right, so just a recap of the problem. Once again, we have a bead which is spinning within the confines of the tube. Of course, the bead is spinning as a part of the tube, which is spinning about the vertical axis at a constant rate of omega. So let's say that omega here is a constant. Okay. All right, and then we have the force of gravity acting. We are told that the contact between the bead and the inner surface of the tube is a rough contact, which means that we are going to have the forces of kinetic friction involved in this problem. So this is a non-conservative system. Okay, that's something that we got to keep in mind right at the beginning itself. Okay, so some key points or strategies for solving. Let's look at it this way. So how to solve this problem? Okay, first thing is this is a non-conservative system. Okay, due to the presence of kinetic friction. We need to determine whether the constraints are holonomic, so that the system is holonomic. That's the second thing. So look at constraints to determine whether the system is holonomic or not. system is holonomic or not. Okay, and as always, we need to identify what the configuration coordinates are. So let us do that by first of all setting up a coordinate frame, and then we will see what the configuration coordinates are, and then we will see what the constraints are, and then based upon that we will use the idea of Lagrange multipliers. All right. So I'm going to take the problem from above, and I'm going to redraw this figure once again. Okay, so I'm going to take this particular setup. Okay, I'm going to copy that and then bring it down here. So we need to set up a coordinate frame. That's something that we got to keep in mind. So this is one thing here. Okay, so to set up a coordinate frame, let me take this point O and slightly scoot it up, write it somewhere here. Okay, so here is the point O, and then I'm going to say that okay, let me cut this piece off here. Let me bring it back out again. Okay, so let me say that the axis that is extended here, this is the z-axis. If perhaps that did not come out too well, but let me redraw the axis here. So let me call this as EZ, if that is okay. Okay, so this I'm going to call as E suffix Z. Okay, then I'm going to set up an EX and an EY axis system, as you're going to be seeing in a minute. Okay, so here is the EX system and the EY system. Okay, so here is one, and then here is the other coordinate frame. And the thing is, what is this coordinate frame attached to? This is a coordinate frame that is attached to the tube itself. Okay, so this is going to be my EX, and this is going to be EY, and then from let me scoot this out a little bit more, and then write that out here. So this is R of t, we know that. Let me drop a perpendicular from the point P onto the xy plane right here. Let me get rid of the gravity force. We know that gravity acts on this problem, so I'm just going to get rid of that. From where the particle is sitting, I'm going to project it onto the EY EX plane. Okay, so here is the situation. Okay, and then I'm going to join the point O to where that intersects the XY plane. And if you want, we can duplicate this, and I'm going to just draw it here so that, well, scoot it out a little bit here so that you see that here is the XY plane. Okay, and I'm just dropping a perpendicular onto that plane. Okay, now complete the figure by joining this with the point O. Okay, so here is that line, and I'm going to draw a line parallel to that, starting from the head of this bead here, so that it intersects the bead axis. Okay, and I have pretty much all the dimensions that I need for my problem to start getting solved. Okay, first of all, I'm going to have a fixed coordinate frame which is outside the frame of the problem. Okay, so I'm just going to say, okay, there is a fixed coordinate frame here, EX, EY, and EZ. This is typically what we do in all of our problems. Okay, this is E capital X, capital Y, capital Z. And then this is E capital Y, and then this is E capital Z. In this situation, you see that the direction EZ is going to be the same as that for a fixed frame. So let me call this observer as some observer A. This is a fixed observer. Fixed observer or a stationary observer. Okay, this is going to be called as frame F1. Okay, this is frame F1. Then I'm going to have this frame F2. Okay, so I'm going to label this as frame F2. Frame F2 is a frame that is attached to the tube itself, and then I'm going to have one more coordinate frame which is going to be given by the following, but before that I need to have some angles which I'm going to show in a minute. Okay, first of all, this angle here between the z-axis and the direction from point O to point P, I'm going to call that angle as an angle theta. Okay, so this angle is the angle theta. It is the same as this angle here. Okay, so that's the angle theta. Then I'm going to have one more angle which I'm going to call as the angle phi, all the way from EX onto the line from the point P to this XY plane. So I'm going to call this angle as the angle phi. Okay, so this is going to be angle phi. All right. Then I'm going to set up a coordinate frame, a third coordinate frame, which is going to be the following. Okay, this is going to be the direction ER. Then I'm going to have a direction that is perpendicular to this, which is going to be called as E theta, in the direction of increasing theta. And for me, increasing theta is drawn in the following manner. Of course, you will see later on that this theta is a fixed angle. So I'm going to have E theta, which is going to be drawn this way. So this is perpendicular to ER. Okay, this is the direction of E theta. And then I'm going to have the third direction, which is the E phi direction, which is perpendicular to the line that is drawn on the XY plane. Okay, so I'm just going to draw that line first here. Okay, this is the direction E phi. I'm sorry, the direction E phi, and I'm going to draw this parallel line, take this line, and then it's not letting me scoot that thing out. Perhaps this is not a good idea. Okay, so I'm just going to draw a line that is parallel to that on this frame here. So this is going to be E phi as well. Okay, so this is going to be E phi. Okay, and so here I have another frame. So this is going to be called as frame F3. Okay, all right, and so I'm going to summarize these frames. So first of all, frame F1, which is E capital X, E capital Y, E capital Z, is a fixed frame. Okay, this is something that you want to see here. Okay, then the second thing is the frame F2, which is E little x, E little y, E Z, is a frame attached to the rotating tube, and we know that the tube is rotating at a rate of omega, so I just want to throw that in to the mix here. So I want to bring that now. So that rotation is omega here, as you can see. Okay, then and you can say that, okay, omega of frame 2 related to frame 1 is going to be omega in the Z direction. And then thirdly, I have frame F3, which is ER, E theta, and then E phi. This is the frame that depicts the motion of the particle. Okay, I'll just write this word again, depicts the motion of the particle. Okay, and if I were to write the angular velocity of frame F3 relative to F2, okay, omega of F3 relative to F2, and bear with me, I'm just going to say that let's assume that this angle theta is not fixed to begin with, and then we will enforce that as a constraint later. We will see that, okay, the angular velocity of frame F3 relative to F2, if theta were allowed to change, would be theta dot in the E phi direction. Okay, if theta were not a constant. Okay, and I want to make a note of the fact that here is the angle theta as well in the initial figure. Let's say that this is the angle theta. Okay, this angle theta, and I want to make another statement here. We will assume that the angle theta is a fixed angle. Okay, this is something that we will notice at the beginning of the problem. Okay, all right, and so omega of frame 3 with respect to frame 2 is known, which means that omega of frame 3 slash frame 1 is omega frame 3 slash frame 2, omega of frame 2 slash frame 1, which means that omega of frame 3 relative to frame 1 is going to be theta dot in the E phi plus, I'm going to say that this is going to be phi dot in the EZ direction. Okay, and you can notice here that phi dot is actually going to be equal to omega, which means that I can essentially say that this statement here is phi dot in the EZ direction, and this is because phi dot is equal to omega. Okay, so this is the reality of the situation here. I have all these frames, and this is the angular velocity of the frame. This is assuming that theta is not fixed. Okay, now we are going to enforce the constraints. Okay, so what are the constraints? And now we're going to look at the constraints. Okay, the first constraint is that theta is fixed, which means that theta dot is equal to 0. The second constraint, as you can see, is that phi dot is actually equal to omega. Okay, and using these constraints, we can very well say the following: omega of frame 3 slash frame 1 is actually equal to omega in the EZ direction. Okay, so this is something important. So these are the two constraints that we have right here. Okay, now we have to decide whether the constraints that we have are holonomic or non-holonomic, but before that we need to set up configuration coordinates and so on. Okay, so what are our configuration coordinates? Okay, configuration coordinates for this particular problem. Okay, configuration coordinates are the total number of coordinates which are used to locate the position of this particle or this bead in the absence of any constraint. Okay, so for us the configuration coordinates are going to be 3, because this is a system in 3D. The configuration coordinates are r of t, theta, and then the angle phi. Okay, so I'm going to say that these are our configuration coordinates. So these are r of t, and then theta, and then the angle phi of t. Okay, I can also call this as theta of t. It does not make a difference to me. Okay, I'm going to call r of t as let's say q1, but then we will revert back to writing it as r, theta, and phi. Okay, this we shall call it as q1. Let's call this as q2. Let's call this as q3. Okay, now we are going to write the constraints in the Pfaffian form. Okay, constraints in the Pfaffian form. We have two constraints. Okay, so j is equal to 1 is the first constraint equation. Let me rewrite this word again. This is the first constraint equation. And this equation is theta is equal to a constant. Okay, which essentially implies that theta is q2 for us. So this is q2 is equal to a constant, which implies that q2 dot is equal to 0, which implies that dq2 by dt is equal to 0, right? Which essentially tells me the following. So j is equal to 1. The Pfaffian form of that first constraint equation is 0 times dq1, then 1 times dq2, 0 times dq3 is equal to 0. Okay, this is the first constraint equation in the Pfaffian form. So let me put a box around it. Okay, let me duplicate that and bring it down here. and complete the box, and one more here. Okay, so this is the j is equal to 1 Pfaffian form. Okay, I just want to see if I can scoot that guy a little here. Maybe I should get rid of this guy and expand this a little more, likewise here, and then join these two. Okay, this is the Pfaffian form of the first constraint. Now I got to do the same thing for the second constraint. Okay, so the j is equal to 2 constraint is the second constraint equation. Okay, this is the constraint equation that phi dot is equal to omega. Okay, and this implies that phi dot is actually q3 dot. So q3 dot is equal to omega, or dq3 by dt is equal to omega, which tells me that dq3 is omega dt, or if I rearrange this, the j is equal to 2 constraint is the following. Okay, j is equal to 2 constraint is 0 times dq1, and then 0 times dq2 plus 1 times dq3 minus omega dt is equal to 0. Okay, so this is that equation. Let me copy some of these and bring them down here so that we can box this expression as well. Okay, and completing the box here with a different color. Okay, so we have these two constraint equations, and the idea is, of course, we can say by inspection itself that these are holonomic constraints, or you can do the test for integrability to prove that they are holonomic constraints. So I'll leave that as an exercise. Okay, left as an exercise, to use the test for integrability to prove that the two constraint equations above are holonomic. Hence, all the constraints are holonomic. Which implies that the system is a holonomic system. Of course, we still have to use the idea of Lagrange multipliers in this problem, so this is not going to be a very useful piece of news, but in case you wanted to obtain only the equation of motion, you can actually come up with a generalized coordinate, and as many of you might have guessed, this is going to be r of t. Okay, so in case we were asked to come up with a generalized coordinate to solve for the equation of motion, to obtain the equation of motion, that would be r of t. Okay, but we are not going to be doing that. Okay, all right, so we have the situation that q1, q2 and q3 are r, theta and phi, and then we have these two constraint equations. We have to use the idea of Lagrange multipliers. And what I'm going to do is I'm going to say that, okay, in order to look at what's happening in the problem a little better, I'm just going to make use of r, phi and theta instead of q1, q2 and q3. Okay, so just as a way of looking at this more clearly, okay, just a quick note to see what is happening. Sorry. More clearly, I am going to use, or I am not going to use Q1, Q2, Q3, but instead will use Q1 is equal to R of t, Q2 is equal to theta of t, Q3 is equal to phi of t, to obtain the Lagrange multipliers. Okay. All right. And to use the Lagrange formulation, we first of all need the kinetic energy and the potential energy. So let's go for that. Okay, so let us next obtain the kinetic energy and the potential energy. For the particle. All right, to obtain the kinetic energy, we actually need to obtain the velocity of the particle. That's fairly straightforward, as we have seen in many problems, but let us, of course, go forward and obtain it. Okay, so for this I need my figures from before, so let me copy this figure down, and we have the following. Okay, so I'm going to take this entire figure with the coordinate frame that I have there. Okay, so I'm going to copy that, and I'm going to bring that down here, and I'm going to paste it. I'm going to shrink the size of this a little bit so that we can make use of the figure. I'm going to get rid of these frames 3, 2, 1, and so on. Okay, maybe I can shift them a little somewhere. I guess I can't do that. Anyways, so here is what I'm going to be doing. Okay, velocity of point P is velocity of well, with respect to the fixed observer, it is with respect to the point O, and then there is some relative velocity term that we have to account for. Okay, so velocity of point P, or let's say position vector of point P. So Rp slash A is Rp slash O plus Ro slash A. So this is the vector equation, and then you notice that the point O is a fixed point, which means that R dot O slash A is 0, which essentially tells us that velocity of particle P is just going to be R dot of P slash O. Okay, so this is going to be d by dt of R of t ER. Okay. Now R of t is a function of time, because as you can see the particle can slide back and forth, and ER is also going to be rotating over time, right, because it's fixed to the particle, and the particle is spinning along with the tube. So we have to do time derivatives for both of them. Okay, so this tells me that Vp is going to be R dot ER plus R E dot of R. Okay, ER is a part of frame F3, as you can see, so this can be written as R dot ER plus R times omega of F3 slash F1 crossed with ER. Okay, this is the term E dot R. Okay, all right, and then what is omega of F3 slash F1? We have that from the beginning of the problem. So Vp is going to be R dot ER, and then this is going to be R times, instead of writing it as omega, I'm going to write it as phi dot. Okay, so this is going to be phi dot in the EZ direction crossed with ER. Okay, so this is going to be the situation for us. Okay, now you obviously see that EZ is in a different coordinate frame, so I have to do a coordinate transformation between ER, E theta, and EZ. So let me do that very quickly here. Okay, so if I set up EZ, this is going to be EZ. Okay, then I'm going to have ER and E theta. So this was ER. By now, this thing should be fairly straightforward to all of you, I hope. Okay, this is going to be E theta, so this is ER. Sorry, this is E theta. This is a 90-degree angle right there, and this is going to be EZ right here, and this angle here is going to be theta. As you can see from the figure, the angle made by ER with respect to EZ is theta, so this is the angle theta. Okay, I want to show that in the figure as well. This is the angle that I'm talking about. This is the angle that I'm talking about, and I can maybe put an arrow and then point it out onto what I'm talking about here. Okay, that is the angle theta, and I'm going to skip some of these steps because we know how to do this. So if I do this, EZ can be written as cos theta ER minus sin theta E theta. Okay, and so if I do this, VP, if I do the substitutions, is R dot ER plus R times phi dot times cos theta ER minus sin theta E theta crossed with ER, and then I have the triad. If I use the right hand rule, if I do ER crossed with E theta, that's going to give me E phi. Okay, so here is my triad, and this implies that ER crossed with E theta is equal to E phi. This is how the coordinate frame was drawn. Frame F3 was drawn this way. So look at frame F3 for this. Okay, and so if I do the cross product, E theta cross ER is minus E phi, and so the velocity is going to be obtained as the following. So VP is going to be R dot ER, some radial component, and then some component in the phi direction because of the rotation of the tube. So this is going to be R phi dot sin theta E phi. Okay, so this is the velocity. Now what I'm going to do is I want to obtain the acceleration as well. Okay, you'll see the reason for this as we complete the problem further down. Okay, so just for convenience, okay, so for use later, I will obtain the acceleration of the particle as well. Okay, and that is AP, which is d by dt of Vp. Just want to write this t carefully here. This is d by dt, time derivative. Okay, and if I do that, that's going to be R double dot ER, then R dot E dot of R, then I'm going to have R dot phi dot sin theta E phi, and I'm going to have two more terms, which is going to be plus R phi double dot sin theta E phi, then I'm going to have R phi dot theta dot cos theta E phi, and then lastly R phi dot sin theta E dot of phi. Okay, so it's a fairly long expression, and so if I do that quickly, acceleration of particle P is R double dot ER, and then R dot times omega of F3 slash F1 crossed with ER plus R dot phi dot sin theta E phi. Then I'm going to have phi double dot is going to be 0, so I'm going to strike that term off. This is 0. This is because phi dot is equal to omega is a constant. Okay, so note here, phi double dot is equal to omega dot is equal to 0. This is because omega is a constant. Okay, so that's the reason why that term gets knocked off. Then I have two more terms, which is going to be r phi dot theta dot cos theta e phi, and then I'm going to have r phi dot sine theta omega of f3 slash f1 crossed with e phi. Okay, this is the entire acceleration term. I have to of course substitute for omega of f3 slash f1. Omega of f3 slash f1 is phi dot ez, which is phi dot due to the coordinate transformation above cos theta er sine theta e theta. Okay, substitute into that. Okay, and I'm going to skip some steps. After skipping the details, we end up with the following. Okay, we obtain the following. Okay, velocity of p from before is r dot er, and then r times phi dot sine theta e phi. Okay, so that's one thing that we have obtained. Then acceleration of p, it's going to have the following terms in it. So I have done this calculation before, so I'm just going to copy that result here. This is going to be r double dot minus r times phi dot square times sine square theta er. This comes from that omega cross e phi term. Okay, then I'm going to have plus minus r omega square times a sine theta cos theta term in the e theta direction. Okay, and then lastly I'm going to be having something in the e phi direction, which is 2 r dot omega sine theta in the e phi. Okay, so this entire thing is the acceleration expression. All right, so we are now ready to write the kinetic energy, the potential energy, and then go forward with the solution of this problem as well. Okay, so kinetic energy T. And an important thing that you're realizing in this problem is, you see, because I have to compute the constraint forces and so on, I'm actually using the configuration coordinates to write the kinetic energy and the potential energy. So I just want to make maybe a quick note of that before we proceed. Okay, so a quick note. Okay, because we want to obtain the constraint forces by using Lagrange multipliers. We will write the kinetic and potential energy terms, kinetic energy and potential energy in terms of the configuration coordinates. Okay, so whenever you see the term Lagrange multipliers, you will have to use the configuration coordinates in order to obtain the kinetic and the potential energy. This is valid for a holonomic or a non-holonomic system. If you have a non-holonomic system, you don't have a choice. You just have to use the configuration coordinates because you cannot obtain a generalized coordinate. But if you have a holonomic system, you have a choice. Okay, you either use the generalized coordinate, then you don't need to obtain the constraint forces. You don't use the Lagrange multipliers. But if you're using Lagrange multipliers, you got to use the configuration coordinates. Okay, so we will summarize all of these at the end. Okay, hopefully by the end of this lecture. All right, I'm going to proceed and write the kinetic energy. So T is half m vp square, and in this situation, for us the rotational kinetic energy is 0. Is 0 because we have a particle. Okay, so that's something to keep in mind, which means that T is going to be half times m times vp square. Look at vp has two components, so r dot in the er and then something in the e phi. You got to make sure that the velocities are in the same coordinate frame. I cannot have a velocity term in ez and then another velocity component in the e phi direction. I have to do a coordinate transformation. Okay, so make sure all of these are in the same coordinate frame. Either the f3 frame or the f2 frame or the f1 frame does not make a difference. They have to be absolute vectors and they have to be in the same coordinate frame. So that's something that I also want to make a quick note of here. Okay, so note, okay, velocity vector has to be in the same frame. Velocity vector components have to be in the same frame. Okay, velocity component, let's say that these are the components. Okay, velocity components has to be in the same frame. Okay, and of course by the end of this we will summarize all of these as well when we write up the Lagrange formulation. Okay, so this is half mv square. So if I do v square, it's going to be r dot square phi dot square sine square theta. Okay, so this is going to be the following: r dot square r square phi dot square sine square theta. Okay, this is the kinetic energy. The potential energy is fairly straightforward. If we go back to the figure, okay, so I had a better figure here at the beginning when we drew the situation. Okay, so the potential energy is going to be a positive energy from the xy plane, exey plane, all the way to where the particle p is sitting. It's going to be r cosine theta. So let me write that dimension down. So this dimension here all the way from here on to there, which is the same as that height. Okay, this is going to be r times cosine theta, or the height h. Okay, so let me specify that here too. Okay, this is the height h, which is equal to r times cosine theta. Okay, and this is r sine theta because it's a right angle triangle, of course, as you can see. Okay, all right. So going back to our problem, V is going to be mgh, which is mgr cosine theta, and note that h is the height of the particle. Sorry. From the ex ey plane, which is the datum plane. Okay, so I have the potential energy to kinetic energy. Just time to write the Lagrangian. So L is equal to T minus V, which means that L is going to be half m r dot square, half m r square phi dot square sine square theta, minus mgr cos theta. Okay. So important thing here, we just have to now collate all our equations. We have to use the multipliers and so on. So here is what we got to do. Okay, so we have to use since we are using multipliers, we need to write the constraint equations in the Pfaffian form. Okay. And we have the constraint equations already written in the Pfaffian form, so I'm just going to bring them down here, but instead of writing it in terms of q1, q2 and q3, I'll just rewrite them in terms of r, theta and phi. Okay, so this is going to, I'm going to copy that, and then I'm going to bring that here. Okay, so this is the first constraint equation. Okay, this is j is equal to 1. I'm going to rewrite the above in terms of q1 is equal to r, q2 is equal to theta, q3 is equal to phi. This is done purely for the sake of simplicity. Okay, for the sake of simplicity. Okay, this is not done for, typically I don't do this for problems. Okay, so in this situation, if I do that, then I have j is equal to 1. This is the constraint number. Okay, this is constraint number 1. Then I get the following: 0 times dr, 1 times d theta, 0 times d phi is equal to 0. Okay, which means that these coefficients, okay, I'm going to write them now as the following. Okay, so I have 3 of them. This is going to be a1r, a1 theta, okay, and a1 phi is equal to 0. If I had used the original form dq1, dq2, dq3, then these guys would be called as a11, that's a12, and of course this is a13. So this is the same as a11, a12, a13. Okay, this is the same as a12, same as a13. Okay, this is for the first constraint. Then I do the same thing for the second constraint as well. I'm just going to bring the constraint down from the previous location where it was written. Okay, so bring this creature down. All right, and I'm going to come and throw that fellow here. Okay, so this is the second constraint for me. Okay, and once I have this, then I'm going to rewrite this once again in terms of theta, r and phi. Okay, so I'm going to rewrite, sorry, this is the wrong color, rewrite the second constraint as well in terms of r, theta and phi. It's the same thing. I mean, you can or you don't need to do it if you are not if you're okay with not doing it, that's completely fine. Okay, so this is j is equal to 2. This is the constraint number. Okay, and then this is going to be 0 times dr, 0 times d theta, 1 times d phi minus omega dt is equal to 0, which means that these coefficients are now going to be the following. Okay, there's one here, there's one here, there's one here, there's also one here. You remember the term AJT, right? That's that particular fellow here. Okay, so this is going to be A2R, which is 0. This is the same as A21. Okay, if I had it here, this would have been called A21. This is A22, A23, and this is actually A2T. Okay, This creature here is a2 theta, which is 0, and that's the same as a22. Then this is going to be a2 phi, which is 1. This is the same as a23, and then this is a2t, which is omega. Okay, so we have everything written down, and what I want to do is I want to first write the Lagrange equations using the multipliers for r, theta and phi, and then we will collate all the information that we have and get going on the problem. Okay, so the next step is to write the general Lagrange formulation using configuration coordinates and the Lagrange multipliers. Okay, so this is our next step here. All right, here is what we're going to be saying. So the general equation is the following. So for the ith configuration coordinate, here is what we have: d by dt of dl by dqi dot is equal to dl by dqi plus qi non-conservative, if we have any non-conservative forces or torques, which we do in this problem actually, plus summation j is equal to 1 to m, this is the constraint number, lambda j aji. Okay, for us, here is the situation. So for our problem, for our problem, here is what we have: I is equal to 1 implies that q1 is the same as r. This is the configuration coordinate, and our equation is going to be the following. Okay, d by dt of dl by dr dot is dl by dr plus qr non-conservative plus summation j is equal to 1 to 2, because we have two constraint equations, lambda j aj, and this is I is equal to 1, so I'm just going to say that this is aj r. Okay, then I is equal to 2, which implies that q2 is equal to theta. I have d by dt dl by d theta dot, which is equal to dl by d theta plus q theta non-conservative plus summation j is equal to 1 to 2 lambda j aj theta, and then I is equal to 3 is q3, which is phi, and typically I just want to mention that I would have written this in terms of q1, q2, q3, but after some time it is very hard to know what is q1 and q2 when you're deep down in the problem, so it's better to see it in terms of r, theta and phi. Okay, that's the precise reason I'm using r, theta and phi. This is not the best way of doing it using q1, q2, q3 is the way that most dynamicists worth their salt will be doing it. Okay, but this is just to make it a little more simpler to look at. All right, and this is d by dt of dl by d phi dot, which is dl by d phi plus q phi nc summation j is equal to 1 to 2 lambda j aj phi. Okay, so this is what we have. Then I just want to make a quick note. Okay, what are our forces? Okay, what are our non-conservative forces? For us, only one non conservative force. This is the kinetic friction force between the bead and the tube. Okay, and this is fairly easy to see if I go back to the figure. Okay, the figure of the bead and the tube, maybe a slightly bigger figure here. If I go back to this figure, I see that the bead is going to be sliding in the radial direction only, which means that the kinetic friction force is going to be in the direction ER. Okay, of course it's going to be either in the positive or negative ER direction, depending upon the sign of the velocity of the particle relative to the tube. Okay, all right, so here is what I'm going to be saying. Okay, the direction of the kinetic friction force is opposite to the direction of the relative velocity between the bead and the tube. And so Vp relative, as you can see, if I fix the tube, what is the thing the bead is going to do? The bead is just going to slide in the ER direction, right? So Vp relative is just going to be R dot in the ER direction. Okay, if you fix the tube, the bead slides relative to tube in the ER direction. Okay, which tells me that okay, if I write the friction force now, so F mu K, if I write the friction force, this is going to be minus mu K times the normal force, and then this is going to be dependent on the sign of ER dot. Okay, some sign of R dot, and then in the ER direction. Okay, opposite to the direction of the relative velocity. Okay, this is opposite to direction to Vp relative. All right, fantastic. So we got everything going for us. Then the other thing we got to see is, okay, you also want to see what is the position vector where the force is acting. Position vector for the force F mu K from point O on the tube. This is fairly straightforward, right? We know that this is going to be R for that force is going to be RER, okay, which implies that R dot is R dot ER, or E dot of R, or R dot is just going to be R dot ER plus R phi dot sine theta E phi from before. Okay, all right, and then we're going to now do the following. QR non-conservative is going to be F mu K dotted with dr dot by dr dot. Okay, R dot is the position of the force, so let me just write this as R dot of the force F. Okay, this is the force F, this is where the force F is acting. Okay, and this is going to be minus mu K times N times sine of R dot ER dotted with d by dr dot of R dot ER plus R phi dot sine theta E phi. All right, which tells me that if I do the math, QRNC is just going to be minus mu k times n times sine of r dot. Okay, then likewise Q theta NC is going to be F mu k dotted with, and I'm going to skip some of these steps. These are velocity dependent forces, which is why we are doing the dr dot. Okay, this is going to be d theta dot, which will end up being 0. Likewise Q phi NC is going to be F mu k dotted with dr dot of F by d phi dot is equal to 0. And maybe make a quick note here. Okay, these are all velocity dependent. Okay, note, we are dealing with velocity dependent non-conservative forces here, which is why you have this r dot here, and likewise you're going to have that term there, and likewise you're going to have that term there. Okay, all right, so now we go back to our Lagrange equations that were written earlier, and then we can strike off some of these terms. So this term is going to be gone, that term is also going to be gone, and so let me bring out some of the other things that we have here. Let me collate everything, and then let's start doing the differentiations and so on. So bring everything together. Okay, I have the Lagrangian L is half m r dot square plus half m r square phi dot square sine square theta minus mgr cos theta. That's one thing. Then for j is equal to 1, I have a1r is 0, a1 theta is 1, a1 phi is 0, j is equal to 2, a2r is 0, a2 theta is 0, and a2 phi is 1. Okay, that's something that we found out. And the third thing is QRNC is minus mu k times n times sine of r dot. Then Q theta NC is 0, Q phi NC is 0. And we see that because we have two constraint equations, we're going to have lambda 1 and lambda 2, two multipliers. Okay, so something that I want to make a note of. Okay, we have two constraint equations. Okay, so since we have two constraint equations, we will have two multipliers, two Lagrange multipliers. So number of Lagrange multipliers is always equal to the number of constraint equations. Two Lagrange multipliers. Okay, so typically number of constraints is equal to the number of multipliers. All right, so we go forward, and we start looking at each of the equations from before. Okay, so let me start off with the first one. So first one is the R equation. Okay, so I have d by dt of dl by dr dot is equal to dl by dr plus qr NC, and then I'm going to start expanding this summation term from before, so that's going to be lambda 1 A1R, lambda 2 A2R. Okay, that's the first one. Then the second one in the theta direction is d by dt dl by d theta dot is equal to dl by d theta q theta nc lambda 1 a1 theta lambda 2 a2 theta. And then third one, phi d by dt of dl by d phi dot is dl by d phi plus q phi nc lambda 1 a1 phi lambda 2 a2 phi. And I'm going to start knocking off some of these terms right away. Okay, so first of all, the non-conservative forces in the phi and the theta configuration coordinates are gone. A1r is 0, as you can see from there, so this term is completely gone. A2r is also 0. A2 theta is 0, as you can see from above, and then A1 phi is going to be 0 for us. Okay, so a lot of things are cancelling off. All right, and then I start performing these substitutions. Okay, so start substituting. Okay, so look at our equation. I'm going to have d by dt of dl by dr dot. So if I go back to the Lagrangian terms containing r dot, there is only one, so that's going to be mr dot. Okay, if I do the differentiation, so this is mr dot. This is equal to dl by dr. Go to the Lagrangian once again. There are two terms containing r. There is mr square, phi dot square, sine square theta, mgr cos theta. So that's going to be mr. The factor of 2 will be gone. The factor of half will cancel off with that. So that's mr phi dot square sine square theta. Okay, so this is going to be mr phi dot square sine square theta. Okay, so that's one thing that will come out of that. All right, and then I'm going to have minus mg r cos theta. Instead of the r is just going to be mg cos theta. Okay, so that's going to be minus mg cos theta. Okay, and I'm going to have q rnc. qrnc we found out was minus mu k sine r dot times the normal force, so that's going to be minus mu k times the normal force times sine of r dot. Okay, which means that if I now expand this, this is going to be, and I cancel off the m terms on all sides, so I get rid of that. So that's going to be gone, that's going to be gone, that's going to be gone, and that will be divided by a factor of m here. So if I polish it off, I actually get my equation of motion. Why? This is because, you see, if I look at the expression above, it does not contain any constraint forces. Okay, constraint forces. So this is actually the equation of motion for me. Okay, and so if I expand it, this will tell me that the equation of motion is the following. R double dot, because it's the d by dt of r dot, this is going to be r phi dot square sine square theta minus g cos theta, okay, minus mu k times n by m sine of r dot, which is coming from the friction force. So I just want to put a quick box over this expression here. Okay, and let me duplicate that and bring that creature down here, and then complete the situation. So this is going to be my equation of motion. So if I had started off by choosing a generalized coordinate, this is the only equation I would have obtained. Okay, so I just want to make a note. Okay, if we had solved the above problem using a generalized coordinate, which is r of t, the above equation is the only equation we would have obtained. Okay, that is something to keep in mind. And I can also make a substitution. I can say that phi dot is actually equal to omega. We can say that phi dot is equal to omega, which means that the equation of motion is a nicer, much more fancier expression, which is r double dot is equal to r omega square sine square theta minus g cos theta minus mu k times n by m times the sine of r dot. Okay, so this will be the actual equation of motion, but we are not done. We have some of the constraint forces and so on to be calculated as well, so we have to go forth and get that. Okay, now look at the theta and the phi equations. Okay, so we started off with the r equation, so I'm going to look at the theta equation. Okay, so the theta equation, if I just rewrite that, after cancelling of some of the terms, we have d by dt of dl by d theta dot is equal to dl by d theta plus q theta nc, and then lambda 1 a1 theta, lambda 2 a2 theta. We had knocked off some of these terms. This was also gone, and a1 theta was equal to 1 for us. So if I do the substitutions, here is what I end up getting. Okay, so this tells me that d by dt of dl by d theta dot. If I go back to this expression of the Lagrangian here, you see that I don't have any terms containing theta dot, which means that that is completely going to be 0. Okay, so that's going to be d by dt of 0. This is going to be dl by d theta. Now you got to be a little careful here. Okay, dl by d theta, if I go back to the Lagrangian, there is a sine square theta, there is an mgr cos theta, so cos theta becomes minus sine theta, negative negative positive, sine square theta chain rule, 2 sine theta cos theta, factor of 2 is gone. Okay, so this is what I end up getting. I end up getting mr square phi dot square sine theta cos theta plus mgr sine theta plus lambda 1 times 1. This is because a1 theta is equal to 1. Okay, which tells me that lambda 1 plus mgr sine theta plus mr square phi dot square sine theta cos theta is equal to 0. So this is one equation that I have to start messing around with. Okay, so this is what I get from the theta expression. So if I duplicate that and I put a box around all of these creatures, okay, let me do that. Slide that here a little more. Still getting used to drawing these at a faster pace. I'm not very successful. Then I go for the phi equation, and then we will analyze the rest of them. Okay, the phi equation is d by dt dl by d phi dot is equal to dl by d phi q phi nc lambda 1 a1 phi lambda 2 a2 phi. Cancel off some of these terms, this is gone, and a1 phi is also gone, and then you will see that the Lagrangian is independent of phi. L is independent of phi, which means that this term is also gone, and so I have the following now: d by dt of dl by d phi dot. Now be very careful. If I go back to the Lagrangian here, okay, I passed it by, there is one term containing the phi dot. Okay, there is one term containing phi dot, so I have to do the differentiation of that. So I end up getting 2 phi dot factor of 2 is gone there, so this is mr square phi dot sine square theta. Okay, so this is d by dt of I'm sorry, I'll write it in black color, m r square phi dot sine square theta. This is equal to lambda 2 times 1, and this is because a2 phi is equal to 1. If I use a chain rule and I get the following, okay, 2m r dot phi dot sine square theta is equal to lambda 2 of 1, which implies lambda 2 is actually 2m r dot phi dot sine square theta, and I'm going to put a box around this as well. Okay, so here is the box. Now what we want to do is, okay, we want to unpack and see what exactly are these lambda 1s and lambda 2, what do they really mean. Okay, so we got to unpack and see what lambda 1 and lambda 2 mean. Okay, and this can be done only by taking a look back at the acceleration expression. Okay, so we have to go back, so go back to the acceleration expression for the particle. Okay, and I just want to bring that expression back down here. Let's write this in the next page. So I think this was written, let me pull that down here. Okay, pardon me for sliding back and forth, but here is the expression. So here is the acceleration expression that I have. I'm going to copy that. Okay, and I'm going to drop that here. Okay, so bringing back, so we're going to do that, and we're going to draw a couple of figures to explain what lambda 1 and lambda 2 mean. Okay, first of all, by inspection, what are our constraint forces? These are nothing but the normal force, right? I mean, the tube and the particle are in motion. The particle is moving relative to the tube, so there is friction between the tube and the particle in the radial direction. So this means essentially I'm going to have normal forces in the theta and the phi direction. These are essentially normal forces n theta and n phi in the theta and phi directions. This is what we actually want to find out. Okay, so we want to find out n theta and phi from using lambda 1 and lambda 2. And this is one of the drawbacks of the Lagrange multiplier method. It is that, in order to understand what these constraint forces are, you have to go through a lot of hoops, pun intended, and you got to really know what you're looking for. So if at all, if I were asked to solve this problem by any means possible and I had to find the constraint forces, I would use the Newtonian way of finding these things. Okay, so let me now draw a figure, and then let us mark some of the forces of interest for us, and then let us bring back the multipliers from the above calculations, and then see what's going to happen. Okay, so I'm going to draw the following figure now. Okay, so I had this figure drawn on my paper, so I'm just going to repeat that here. So here is a situation. Let me draw this in the black color. So I have the z direction here. Okay, then here is the particle which is sitting, I'm sorry, Okay, so here is the particle. Let me draw the particle. Okay, so here is a particle that was sitting here. Then we had the ER, E theta and E phi direction. So I'm just going to continue forth and then draw the ER direction here. So this is ER. Okay, and then perpendicular to that was E theta. Okay, so this was the E theta direction. And I'm also going to draw the following two lines. Okay, first line is starting from here. You will go back to our figure. You can see these lines as you go to our figure. Okay, so I'm going to copy that and then duplicate that and bring that here. Okay, so that, and I'm going to take that, duplicate that, and bring that here, and I'm going to slowly reduce the length of that guy. Okay, of course that's a right angle triangle right there, as you can see. Okay, so this is a 90-degree triangle. So first of all, here is a 90-degree triangle. That's 90 degrees there. I should draw that a little better. I'm sorry, there is no redo button here. I see. That's something that kind of makes me frustrated sometimes. I do. That's 90 degrees right there. And then I have another 90-degree angle right here. So that's 90 degrees as well. Okay, so that's 90 degrees. It doesn't look like 90, but it is 90. Then this is the distance r, okay, to the particle. So this is the point O, this is the point P where the particle is sitting. Then I'm going to do a couple more things. Okay, I'm going to say that, okay, this direction here is the E1 direction. I'm just going to continue with this line and say this is the E1 direction. Then right here, as you can obviously see, this is going to be EZ. This is the EZ direction. EZ direction here, and then the E phi direction is perpendicular to this line here. Okay, this is the E phi direction, and I'm going to take that line and then duplicate that and bring that down here, and I'm going to extend that. Okay, maybe a little more. Okay, I'm going to extend that, change the color to make it the same as that color there, and that is also E phi. Okay, that is also the E phi direction. And one important word to notice here is that this angle, which I'm going to draw in the magenta color, right here all the way to there, okay, that is a 90-degree angle as well. Okay, now I'm going to draw some forces. Okay, these forces, I hope I can draw them in a nicer color here. So let me first draw the force along the phi direction. Let me draw the force along the theta direction. So here is the force along the phi direction. I'm just going to call this as a normal force. Okay, this is N phi. This is a normal force along the phi direction. Then I'm going to have a force along the theta direction. I'm going to call this as N theta. Okay, this is the force N theta, and of course I'm going to have I'm going to take this P and then bring it inside here. Okay, this is the particle P, of course, and I'm going to have the force of gravity, which is acting vertically down, as you can know. Right, this is the force of gravity which is acting vertically down. So that's right here. This is going to be mg. Okay, and then I'm going to bring in the acceleration expression, which we had written sometime back here. So I'm going to scoot that up and maybe bring that down here. Okay, so here is the acceleration expression from before. So I just want to make a note of that. This was obtained from before. Okay, this is the acceleration expression, and what I'm going to do is I'm going to call this component of acceleration, which I'm going to circle here, this I'm going to call as a theta. Okay, this is a theta, and I'm going to draw a force which I'm going to call as m times a theta. Okay, All right, and so here is that force which I'm going to be calling as m times a theta. This is going to be directed in the following manner. I'm going to draw that in the magenta color. That's going to be directed along the theta direction. Okay. I'm sorry. That's going to be directed in this direction here. Okay, so that's going to be called as m times a theta, and of course I'm going to have one more term which I'm going to call as a phi. That is this creature here, which I'm going to call as a phi, and you will see that that term is marked in the following figure here. I'm going to call that as a phi times mass times a phi, so m times a phi. All right. So we have the following forces. We have mg, we have n phi, we have n theta. These are the constraint forces. Now here is what I'm going to be doing. Okay, I'm going to sum moments about the phi direction. Okay, so first thing I'm going to do is let us sum moments about the phi direction using the above figure. Sum moments about E phi. Okay, this is the key step that we are going to be doing. That's the first thing that we're going to be doing. Okay, so if I do the sum of moments about the phi direction and set that equal to 0, here is what I'm going to be getting. What are all the forces that are acting which cause a moment about the phi direction? Obviously MA phi is not going to be of any interest to us. Then I see that n theta times a distance of r, if I use the right hand rule, this is going to be in the negative phi direction. Okay, so that's going to be minus n theta times r. Okay, so if I do that, that's minus n theta times r. That's one moment. Okay, then if I look at the force mg times if this is r, and then this angle here is obviously going to be theta. If I mark that, this is theta, so this is going to be r sine theta, this is r cos theta, right? Mg times r cos theta is going to cause a moment about the positive E phi direction, so plus mg r sine theta, right? Mg times r sine theta. Then ma theta, look at that, ma theta times the distance of r, that is going to cause a moment in the positive phi direction as well. Okay, so then this is going to be plus ma phi times a distance of r. Now what I'm going to do is all these distances I'm going to write in parenthesis, mg times r sine theta. So I'll scoot that a little bit. Apologies, I have to just rewrite this quickly, and then this is going to be mg times r sine theta. All of this is equal to 0. That's what I'm saying, right? Essentially all the sum of all the moments about the phi axis, I'm setting that equal to 0. Okay, so which tells me the following: minus n theta times r plus mg times r sine theta plus a theta. I'm sorry, this is going to be a theta. I made a mistake here. This is a theta. Apologies for that. This is a theta. Then that's going to be m times a theta from above is minus r omega square times sine theta cos theta. Okay, and times the distance of r, that is equal to 0. Right, so we see all of these going on, and what I want to do is I want to bring in some of these terms. I have actually drawn ma theta to be pointing in the e theta direction, but then it has to actually be pointing in the opposite direction because it's negative. So I'm just going to be interested in the magnitudes of these terms. Okay, so look at only magnitudes. Okay, I'm going to say that magnitude of n times r is equal to magnitude of mg times r sine theta plus magnitude of m or omega square sine theta cos theta times r, so this is going to be mr square. Okay, now compare this with the theta equation from above. Okay, if I compare this with the theta equation from above, then I get the following. So I take the theta equation from above. Okay, I'm just going to copy this expression here. If I copy that and I bring it down here, okay, if I do that, this is the theta equation. If I look at the magnitudes only, I see the following. Okay, magnitude of lambda 1 is magnitude of mg r sine theta plus the magnitude of m r square phi dot square sine theta cos theta. And you see, obviously, by comparing, if I call this as equation A and if I call this as equation B, by comparing these two equations, equations A and B, we can see that lambda 1 is actually n theta times r. So you see that lambda 1 is actually not the constraint force, but this is the moment of the constraint force about the E phi direction. This is the moment of n theta about E phi, which means that I can now recognize now that having lambda 1 gives us n theta. Okay, which means that n theta is just going to be mg sine theta, if I just look at the magnitude, plus mr phi dot square sine theta cos theta, where I have gotten rid of one of the r values, and so I'll just put a box around this. Okay, so here is what we have. So we have the first constraint force, and likewise we got to do the same thing for the second constraint force. I'm not going to go over the details of it, okay, because I'll be posting the elaborate notes for these problems. Okay, look at from the second constraint equation, or from the second equation for theta, I'm sorry, I apologize for that, from the phi equation. Okay, that's what I wanted to write here. Okay, so from the phi equation, here is what we have. Okay, so if I go back and I bring this creature here, if I copy that and I paste it here, we can recognize, so recognize that the term 2r dot times m times phi dot sine square theta is a moment, right? Because you see that this is going to be a force times a distance r sine theta. So this is actually going to be the acceleration in the phi direction. That is, if you take acceleration, take a phi, which is or if you take m times a phi, which is if you go back here, is 2r dot omega sine theta or phi dot sine theta. This is 2 times m times r dot times phi dot sine theta, and multiply with a distance or sine theta. This is essentially gives the moment about EZ. Okay, and that's what we have here. If you take MA phi, and if I do cross product with r sine theta, then I get a moment about the EZ direction. Likewise, if I take N phi, then if I take the moment about the EZ direction, it has to be multiplied by r sine theta. Okay, so which means that if I sum moments, about EZ from figure above and look at only magnitudes, we get N phi times r sine theta is equal to 2 times m times r dot times phi dot sine theta times r sine theta, and you compare with the phi equation, which is lambda 2 is 2m r dot phi dot sine square theta. Then this tells us that lambda 2 is actually n phi times r sine theta. And so solve for n phi. We get this to be 2 times m times r dot times phi dot times sine theta. So in summary, equation of motion is r double dot, and this is from above. Okay, if I write the equation of motion in the better form that we wrote it, so I can just bring that down here. I don't need to rewrite it. Okay, so I'm just going to copy that and bring that down here. Okay, so this is the equation of motion for us. That's the first thing that we obtained. So equation of motion is a function of r theta phi dot, okay, and r dot and mu k, and then the normal force. This is the first one. And then the second one is n theta. We obtained this as the following. Okay, we had this as mg sine theta magnitude wise. Okay, just writing the magnitudes, mg sine theta plus it's going to be mr phi dot square sine theta cos theta and then third thing is n phi, which we obtained here as 2m r dot phi dot sine theta, and we can make a substitution that substitute phi dot is equal to omega, and n is equal to n phi square n theta square whole to the power 1 by 2 into the equation of motion to obtain the complete solution. Apologies for going a little overboard in terms of the time, but I'm assuming that hopefully this is enjoyable to you, people of dynamics, and if you have any questions, I'll be happy to answer them by email or via Zoom when we have typical class times and office hours. What I'll do is I'll do the summary of the Lagrangian formulation at the beginning of the next lecture. Okay, I don't want to take up any more of your time. I hope all of you are staying safe. Take care of yourselves, and I'll talk to you during lecture 6. All right, thank you.